So, hello everybody. My name is Philipp. I'm an Android developer at Chefkoch, which is a German-based online food platform. For quite some time now, we are turning old UI screens into nice new Compose ones. And while doing so, we sometimes encountered situations where especially long lists of content or animations made our app lagging, especially on weaker devices. That's the reason why I started to research about the problems and created this little talk. So let's talk about hunting for unnecessary recompositions. Before we actually start, I have a small disclaimer. During my presentation, I will show you several examples which are constructed in a way that they fit this talk. That means you won't see much lagging in the examples itself, because the shown examples are really small ones, but I promise you the issues we are going to talk about will help you better understand what's going on in your much larger apps as well. That being said, let's jump directly into a little recap. As some of you might already know, or maybe you heard it in one talk at the conference here, Compose has three phases: the composition phase, the layout phase, and the drawing phase. Or, in other words, what UI to show, where to place the UI, and how to render the UI. In theory, Compose can execute all three phases in every frame. That means when we have some data which is displayed as part of a composable function, and the shown data changes, Compose might start from the beginning and again execute composition, layout, and drawing phase. This process, and especially re-executing the composition phase again, is then called recomposition. As you might imagine, this can cause an impact in performance if we always execute all three phases to show different data. Therefore, Compose is really smart and can skip an entire phase, or even more than one, if they are not needed to react to the data change. But the problem is, there need to be some rules, which we will have a look on later, to define when a phase is skippable. In some situations, it is not that easy for Compose to decide if all rules are fulfilled and the phase can be skipped. In those situations, Compose runs the questionable phases rather than risking inconsistent states. But we as developers can help Compose to better understand if a particular phase can be skipped, and this is what we are going to look at during this talk. We will have different examples where too many recompositions happen, and we could do some small changes to our code to avoid them. But before we start with the first example, we need to know how can we actually check for recompositions. The first solution is to add simple log messages to your composable functions, and every time you see those logs in your loghead, you know that your UI was recomposed. As this might be error-prone and requires a lot of manual work, there's a second solution, the layout inspector. I guess most of you will know this tool. You can find it in the Tools menu of your IDE. And to get information about recompositions, you then need to click this little eye icon here and activate the Show Recomposition Counts option. So with that knowledge, let's jump into the first example. It is called Read of Frequently Changing State. We got a simple screen with a list of numbers, and on the bottom right, you can see a floating action button. When the video starts to play, you might notice that our floating action button changes its background color every time we are at the top of our list and as soon as we start to scroll down. Let's have a look into the code of this small example. We got our composable function called longListScreen, which has a viewModel parameter, and this viewModel provides our UI state. In addition, we are remembering some lazy list state here. Then we have a child composable called numberList, which takes this lazy list state and the list of numbers from our UI state. The numberList composable is then wrapped by a scaffold, and the scaffold holds our floating action button. If you look right here, you can see that we set the background color of the floating action button to some variable called fabColor. So for the sake of completeness, here is the declaration of our fabColor variable. And before we go into more detail, let's have a look what we can see in the layout inspector by using this code. On the left side, you can see the same view like a couple of seconds ago, and on the right side, you can see the interesting part of the layout inspector. As soon as the video starts, it is important for you to carefully watch this line right here. You can see two numbers. The left one is increasing every time our floating action button changes its background color, and the right number is increasing multiple times in between. The left number, or the left column, represents the actual recompositions. So that is every time Compose decided to re-execute the composition phase and therefore also the other phases afterwards. The right column represents the skipped recompositions. Skipped recompositions are the ones where Compose notices some kind of data change, starts to recompose at some point in our layout, reaches the floating action button, and realizes that it is not necessary to recompose the fab because the data change wouldn't affect it in any way. So we can skip it in this case. Don't worry, we will come back to skipping in Compose in a couple of minutes. What you should notice at this point is that we have many skipped recompositions, which is good because they aren't actual recompositions, but maybe we can do some changes to our code to avoid them. So let's go back and have a look at the declaration of our fab color variable. It is set to color.green when some isScrollToTop method returns true, and color.cyan otherwise. IsScrollToTop is a simple extension function of our lazy list state and checks if the first visible item scroll offset and the first visible item index are equal to 0, so we know we are at the top of our list. So far, so simple, right? But this extension function is basically the cost for all the skipped recompositions we just saw. Especially the first visible item scroll offset changes in nearly every frame as soon as we start to scroll. Since we access this value, Compose triggers a recomposition every time the value changes. Luckily, most of the value changes aren't relevant for the resulting background color of our fab, because we only care if the returned result of the extension function changed. So that means both values are equal to 0, or at least one is not equal to 0 anymore. We don't care for all the other numbers the accessed properties may return. Because of that, we see so many skipped recompositions every time we already left the top position of our list and the returned result of the isScrollToTop extension function stays at false. So here's what we can do about this situation. As soon as you access a frequently changing state value, like the offset value in our example, but your UI is changing less frequently than the accessed value, you should make use of something called derived state_of. Derived state_of makes sure to cache the result of the function inside these curly braces and only triggers a recomposition if the returned result changed. So that's exactly what we want, right? Only trigger a recomposition when the background color of our floating action button has to be changed. So with this little fix, let's go back into the layout inspector and see what we achieved. And as you can see, all of the skipped recompositions are gone, and that's it for the first example already. Let's go to the second one. This one is called usage of frequently changing state in modifiers. This time we got a screen which has a button, and every time I click on this button, some progress indicator appears, and after some seconds it also disappears. Looking at the code, we can see we have our screen composable with a view model and its UI state, and then we have a column with a text composable for the headline, a custom child composable called progress, and another one called progress button. The progress composable wraps the circular progress indicator and the text, which is everything that is shown and hidden on button click. This functionality is done via modifying the alpha value of the wrapping column by using animateFloat as state. So let's have a look into the layout inspector and see what we got so far. Every time our progress composable is shown or hidden, we see a lot of recompositions. If you see such a high amount of recompositions, you should always be skeptical if everything is working as expected. So let's go back into our code and have a look what's going on. Based on a Boolean variable called isProgressVisible, our animateFloat as state returns a float value, which is then passed to our alpha modifier. As you might imagine, we shouldn't see so many recompositions here, but only one for the change of the Boolean variable. But where do they actually come from? To understand this, here is a small side fact. As some of you may know, Compose is internally building a tree of layout nodes to represent your UI structure. This tree could look something like this. Building this tree is part of the composition phase. These layout nodes also contain the information about all of your modifiers, like our alpha modifier here. Since modifiers are immutable objects, the layout tree needs to be changed every time the value of a modifier changes, which then results in a recomposition. As we animate our alpha value from 0 to 1 or vice versa, we have many steps in between that trigger many reconstructions of our modifier and result in all the recompositions we just saw. So how do we avoid all the recompositions and shift the change of our alpha value to the drawing phase where it actually belongs? We can make use of lambdas for this. Some modifiers have lambda-based equivalent modifiers, and during composition, the node with the modifier just gets the information about the lambda, and this lambda is executed in the phase where its result is actually needed. That means that our modifier itself does not change anymore after first composition, and we get rid of all the recompositions. In case of the alpha modifier, which we try to use here, there is a graphics layer modifier in which you can change the alpha value, as you can see. Make sure to use the lambda-based variant of graphics layer, as there is also a non-lambda-based one, which wouldn't help here, of course. Now, let's go back to our layout inspector. And as you can see, we only trigger recompositions when our isProgress visible variable is changing. But you can also see we have some more recompositions in our parent composable alpha screen, and therefore some skipped recompositions for all of our child composable functions. Before we have a look into our code to see if we can do something about it, let's talk about two important concepts in Compose: restartable and skippable. The restartability is the foundation of recompositions. It is applicable for composable functions, and if a composable function is restartable, it can serve as a restarting scope, or let's say an entry point, from which Compose will start recomposition and execute it, as well as all the inner functions again. If a composable is not restartable and access data changes, Compose needs to walk up the tree of layout nodes and find the closest restartable parent. That means you always want to try to keep your restart scope as close as possible to the location where you access changing data. In reality, nearly all composable functions are restartable. There are some exceptions, like manually avoiding restartability, but that is another story. The skippability on the other side is, again, applicable for composable functions, and as I already mentioned before, it is the ability of Compose to skip certain composables during recomposition when the input data of this composable hasn't changed, like we saw for our floating action button in the example before. Last but not least, it is important to mention that not every composable function has to be skippable. So with that in our mind, let's go back into the layout inspector once again. As you can see, our alpha screen composable is recomposing 4 times, so we want to find out why. Our progress composable receives the isProgress visible Boolean parameter, as we already know. This parameter is provided by our UI state and is passed to the composable at this point in our code. So what happens is that the actual state read is located here, and so Compose starts to look for the closest restart scope at this point and finds it with our alpha screen composable. Now, you may ask why this enclosing column isn't the nearest restart scope, right? To answer this question, we need to have a short look at the declaration of a column. As you can see, a column is an inline function, which means its content is inlined at compile time and it ends up not being a function itself. That's the reason why it can serve as an entry point for recomposition. By the way, the same applies for things like box and row as well. So going back to our code, we want to find a way to defer the state read so that it only affects our progress composable. And if you remember, our previous issue was solved by using lambdas because lambdas are executed in the phase where the result is actually needed. So why not try to use the same approach for this problem here? We need to change our isProgress visible parameter and make it a function parameter with return type Boolean, pass the value as part of a new lambda here, and call it like a function parameter at this point. If we finally look into our layout inspector, we can see that only our progress composable is recomposing when our state changes, and those changes do not affect any other composable function on our screen anymore. So we successfully fixed example number 2. Let's jump to the third one, which will get a little bit more advanced. It is called Stabilize the Unstable Part 1. This time we have some kind of random number generator. You can see every time I click on this upper button, a new random number is generated, and when I click on the lower button, the currently generated number is added to some kind of history. I can generate multiple numbers without adding them to the history, and I can also add the same number to the history multiple times. If we look at the code, we can see that we got 3 important child composables this time: header, buttons, and number history. The header composable consists of 2 text composables which display the currently generated number. The buttons composable holds our 2 buttons which we just saw, and the number history composable is just showing all the numbers of the history as part of a comma-separated list in a text composable. So let's have a look what we got in our layout inspector for this example. You can see every time I click on one of those buttons, we have multiple recompositions across the whole screen. And it doesn't really matter which of the both buttons I click, they both trigger a lot of recompositions we might have a look on. But if you carefully watched the code before, you saw that we don't access any frequently changing state or something like that. So this example is quite different from the ones before, and you may ask yourselves how we could find out what's going on here and what might be fixed. Therefore, I want to show you the compose compiler matrix. The compose compiler is able to generate reports during compilation which contain some useful insights about all your composable functions. To enable the generation of these reports, you need to add this little snippet to your build.gradle and build your app in release mode with this build parameter. Now, you may ask why it is necessary to build in release mode, right? The reason for that is that Compose is automatically applying some changes in your debug variants, so things like live editing some values without recompilation work. But those changes would affect the outputs of your generated reports and let you look for the wrong things. So it is important that you build in release mode to only see the things that really matter. When you successfully executed the Gradle task, you will find the following files. At first, a module.json with some common stats about your composables, then a composables text file with information about all of your composable functions like skippability and restartability, which we talked about in the previous example, a composables.csv, which basically contains the same information but in a different format, and finally a classes text file with information about all of the classes inside the module. During this presentation, we will use the composables text file and the classes text file. Therefore, I want to explain 2 more terms to you which are important to understand when working with these files: immutable and stable. Immutable is applicable for class types, and it means that no value of any property of the type ever changes after the object has been instantiated. Examples for immutable types are all primitive types like Boolean, integer, or float, as well as strings and all function types. Stable, on the other side, is also applicable for class types and means that the type can be mutable, but the compose runtime will be notified whenever anything changes that will cause different results. By notifying, it means using compose state. So, for example, the mutable state of function to construct a new mutable state. Both categories will simply output as stable in your report, so the report doesn't differentiate between immutable and stable. If a type isn't stable, it will be marked as unstable in the classes text file of the reports, and unstable input parameters for composable functions can cause unnecessary recompositions, as you will see soon. Before we go back into our code, let's quickly have a look on the rules for some type being stable. The first one is the result of the equals method for 2 instances will forever be the same for the same 2 instances. Rule number 2 is if a value of a public property of the class changes, composition needs to be notified. That's what we just talked about when I explained stable types. And last but not least, all public property types of the class need to be stable as well. So now we can go back to our random number generator example and see how we can fix many of the recompositions. I already generated a random number and reset the recomposition information so we can focus on one feature at a time. What we are doing now is we add the same number to the history multiple times. You can see that we have a lot of recomposition stuff going on for this single action. Let's break it down. The recompositions of the number history composable make sense since we change data and want to show this change as part of our UI. The recompositions in our buttons composable are quite okay since we click on one of the buttons, but we will come back to this point later. And the most interesting ones are the recompositions of the header composable. We have no data change which would affect the header when we add a number to the history. So this is definitely something we should have a look into. That being said, let's jump into the code. We got our header composable function, which takes a parameter of type random data. If we have a look into our compose compiler metrics, especially into the composables text file, and look for the header composable, we can see that the compose compiler says our input parameter from the header composable is unstable. For the sake of completeness, here's the definition of our random data model class. Everything it contains is a nullable integer parameter and a list of integer for the history. If we now take our classes text file from the reports and look for the random data class, we can see its parameter history is considered unstable, and therefore the whole class is considered unstable too. Since our composable takes an unstable input parameter, it is not skippable anymore, because compose can't be sure if necessary input data changed or not. So that means the header composable gets recomposed every time any data on our screen is changing. But instead of thinking about how we could make it stable, let's go another step back. We know that primitive types, like integers, are immutable and therefore stable. We can use this here since the only relevant value for our header composable is the current number integer. So let's simply change our input parameter from type random data to int and generate our reports again. And as you can see, the parameter of our header composable is considered stable now, and our composable is finally skippable. Let's do a last check with the help of the layout inspector. You can see we just turned the actual recompositions into skipped ones, which is enough for this example. Of course, you could go ahead and try to also avoid the skipped recompositions, but we rather want to have a look on the other recompositions instead. You can see every time I click on one button, the other one recomposes too, as well as the button's composable itself. That sounds strange, right? So let's have a look into this. At first, here's the output of our compose compiler metrics report. We can see all three input parameters are considered stable, and our composable is skippable. So there's nothing we can get out of this one. But let's go ahead and see how our buttons composable is actually called on our screen. We pass our current number and two callbacks for the click actions. The callback lambdas access the view model. If we now have a look into the classes reports of the compose compiler metrics and look for our view model, we can see it is unstable. At this point, we shouldn't try to change our view model because under the hood, view models aren't stable types. Let's rather look what happens with our lambda here. At compile time, an anonymous class is generated, which could look something like this. As you can see, this generated class takes the view model as a parameter, so we have an unstable input parameter at this point. That's why we are seeing recompositions here. So how can we solve this issue? We need some way to avoid the generation of the new class. One simple way is to use method references instead of lambdas, since method references are stable function types. Another way would be to wrap the lambda by a remember. This is useful if you need to pass some parameter to the called method and therefore can't use method references directly. For our example, method references work totally fine, so we change it. And before we look back into the layout inspector, we want to have a look on one more thing. As you can see here, we are passing our current number as a parameter. This is necessary to disable the history button as long as no random number is generated initially. The problem is that the state read will trigger a recomposition of our button's composable every time current number changes. But we only want to know if the history button is enabled or not and don't care for the actual number, right? So let's change our parameter type into being a Boolean parameter, change the caller side as well, and finally have a look into the layout inspector data. As you can see, all the recompositions for the buttons composable turned into skipped recompositions, and we also eliminated the recompositions which occurred for the other button of the two as soon as I clicked on one. But what you can also see is I only clicked 2 times on every button, and the number history composable has a recomposition count of 4. Clicking the Generate New Number button shouldn't affect the number history, right? So let's have a closer look on our number history composable. The only parameter it takes is a list of integer. The compose compiler metrics report shows the following. Our input parameter is considered unstable. Now, you may ask yourself why a simple list of integer, which looks like it's immutable, is considered unstable. To give you an answer, let's see how we could define number list. If you see this example, you should know that the number list is immutable on the declaration side, but mutable on the implementation side. Since the compose compiler only sees the declared type and cannot know about the actual implementation, lists are marked as unstable. By the way, the same applies for things like set and map as well, so basically all collection types you know. How can we solve this problem? Again, we have 2 options. Number 1 is you could wrap your list by a class which you then annotate with a stable annotation. But keep in mind, the stable annotation is like a contract, so you need to make sure that you take care of all the rules for some type being stable that we mentioned earlier by yourself. Option number 2 is you could use the Kotlin X immutable collections library. There you have things like immutable list, persistent list, immutable set, and so on, which are guaranteed to be immutable. This is the option we are using to continue in our example. So let's change our numbers parameter into being an immutable list, generate our compose compiler matrix, and see our list of numbers is finally stable and our number history composable is skippable. Now we also need to apply the changes to the caller side. Let's change the history property in our UI state model into being a persistent list. A persistent list is basically an immutable list, but offers operations like add or remove, and ensures every time you add or remove an element, it will return a completely new list, and therefore the equals method won't return true, and compose recognizes the change in data. A small note, persistent lists are considered stable since compose compiler version 1.4.0, which might be important if you are using an older one. If we now generate the reports again, we can see all parameters of our model class are considered stable. Unfortunately, the runtime stability is still unstable, and therefore our model class itself too. What's the reason for that? Let's have a closer look on our current number property. And if you think back to rule number 2 of a type being stable, which was if a value of a public property of the class changes, composition needs to be notified about this change, you can see the reason for the lack of stability here. We got a var property of type integer instead of a val. That means our current number can change after the object has been instantiated, and therefore compose marks it as unstable. So let's change this var and make it a val, generate a new report, and finally our random data model class is stable. With all these changes, let's have a last look into the layout inspector. As you can see, the header only recomposes when a new number is generated, the number history only recomposes when a number is added to the history, and the buttons don't affect each other anymore. Again, of course, you could go ahead and try to fix all the skipped recompositions, but we did this before, so let's rather have a look on an example which is a little extension to the current one, and therefore it is named Stabilize the Unstable Part 2. This time we have a slightly changed number history composable. It now takes an object of a wrapper class history data. History data has our persistent list and is part of some model class called random data 2. As you can see, we already applied all the improvements we worked on before, but still our generated report shows history data is unstable. But why? Have a look on this screenshot here. As you can see, random data 2 and therefore history data are not part of the app module, but are located in some separate module which I named lib. To infer stability, the compose compiler needs to be part of the module where your classes are located. That's why all classes from external modules, not including the compose compiler, are considered unstable. To solve this problem, we have 3 options this time. Number 1 is you can create separate UI models with some mapping functions in your app module where the compose compiler is already applied and can inspect the stability at compile time. Option number 2 is if you only have a few simple parameters that you pass into your composable, you could rather pass them directly instead of having a wrapper model class. And last but not least, if the external module is your own one and not a third-party lib or stuff like that, you could add the compose runtime dependency, which is a really small one as it does not contain compose UI stuff, and then you annotate the affected class with a stable annotation. Keep in mind, as I mentioned earlier, the stable annotation is just a contract, and you need to make sure that you care about fulfilling the rules by yourself. So for our example, we simply use option number 3, mark our history data class with a stable annotation as we fulfill all the rules, and now we can see in our report that the history data class is stable and our number history composable is skippable again. We won't look on the layout inspector this time, so you need to trust me that the solution works. Before we finish this talk, I want to give you a last short advice. Don't try to make your entire UI skippable and all class types stable. You should rather watch out for performance issues and think about if changes are worth. Trying to simply make all class types stable and all composables skippable might introduce new bugs that are hard to debug and will make your code harder to maintain. Under the hood, Compose is trying to take care of as many things as possible automatically, which means everything you saw today, especially things in examples number 3 and 4 about Compose compiler metrics, should only be used to investigate actual performance issues. That being said, we came to the end of the presentation. I got some additional links to different blog posts about the topic, which helped me a lot during my initial research. Yeah, take a picture. Yeah, that's it. Thank you for coming. I hope you liked it.